Hello, everyone. Welcome to this video that is associated with my Journal of Marital and Family Therapy article entitled Estimating Diet Level Processes in MFT Research, General Overview of the Common Fate Model and Extensions into Mediation, Moderation, Growth, and Hybrid Models. In this video, I am going to be going over the common fate moderation model, except in this video, unlike the other two, I am going to switch estimators and we will begin to talk about using Bayesian estimation for estimating and interpreting the common fate moderation model that uses latent interactions. So there are two ways of doing this in maximum likelihood. Your traditional SEM estimator that I go over in two previous videos. You have latent moderated structural equations, and then you also have, the product indicator approach. Right? And so again, in this video, we're going to change up the estimator and focus on the use of Bayesian estimation. So much like the common fate moderation model with maximum likelihood, we are first going to start with a main effect only model using Bayesian, right? So I'm actually going to scroll down and we're going to start in this analysis command. If you are interested in kind of what the variables are and things like that, in the first video in this series where I just go over the baseline common fate model, that's when I go into more of the nuances around introduction to M plus, variable naming conventions, and things like that. So if you find yourself a little out of sorts, then starting there would be a good place. Right? So what we're going to do is we're going to scroll down to the analysis command because that is where we are going to begin to see some of the differences. Up to this point, if you've watched the maximum likelihood videos, everything up here and up is exactly the same as in those other videos. There's nothing actually different. But in the analysis command is where we begin to get things shift a little bit. All right. So by default, M plus is going to have maximum likelihood, going to be your estimator. All right. So we are going to override that default and say estimator is Bayes. So we are again going to use the Bayesian estimation. And then we are going to use or enter in the FB iterations. So essentially a way of thinking about these FB iterations is kind of like bootstrapping from like a frequentist perspective. It's not exactly the same thing, but again, it's going to be like an iterative process to try to find the most likely parameter estimates. Again, one of the differences in Bayes is that they don't necessarily view the population parameter as fixed. Rather, they view it more from like a distributional perspective. So rather than the population for the effect of relationship mindfulness on dyadic coping being 0.34, they're going to estimate instead a distribution of different estimates ranging perhaps from 0.30 to 0.38. I'm just making up some arbitrary numbers here. All right. And so again, Bayesian is again more focused on probabilities and not viewing things as fixed. All right. So with Bayesian estimation, I'm not necessarily going to all the nuances or provide an introduction to Bayesian estimation because we can get down some rabbit holes pretty quickly with Bayes. But I want to give you at least just a general framework for how to understand some of the things that I will be talking about. All right. So again, we'll put generally a large number of iterations here. And so another way you can kind of think about FB iterations and some messages that you'll see in the output is if you've done latent class or latent profile analyses with M plus and using maximum likelihood, they're always going to see a message saying, increase the start values, increase the start values, increase the start values. Where we're going to get the same message for increasing the FB iterations, right? So we're going to use a relatively small number of FB iterations. You'll see some variation. Again, this becomes more computationally demanding the more and more and more you include. But in this video, I'm just going to go over with like 25,000. All right. And so I would normally typically up this to maybe even 50,000, or I've even run some analyses 100,000, depending on model complexity and things like that. Right? So what you will want to know is that M plus discards the first 50% as kind of like a burn-in period. So we're really only estimating 12,500 different iterations of all of the different parameters that are in this model. All right. All right, so we will again move towards the model syntax, and you'll see it is identical to maximum likelihood. We make literally no changes in the model syntax because we're estimating the exact same model, but the change that we're implementing is just in the estimator of the model. All right. And then down here, you will actually see that we have made one small change, and that's with the C interval, where I've added HPD. So M plus has, I think, two or three different ways of calculating the confidence intervals for the posterior distribution in Bayes, and HPD is one of those options. It is not the default. The default in M plus, to the best of my knowledge, is an equal tail indicator that calculates those 95% confidence intervals. So you're gonna have the tails be the same size. Whereas in HPD, you're actually allowing those tails to be asymmetric. All right. And so essentially what we're doing is we're looking for the highest probability density. That's what that's going to be standing for. And there are some resources in on the M plus website that dive more into the different options you have for calculating your confidence intervals. But this is the option that we will be using. Right? And so for this one, I'm actually going to run it. And so you can kind of get a sense of how long it takes. I'm actually going to increase my processors. So it will go a little bit faster, because this can take some time, and it'll take even more time when we add in those latent interactions, right? So as you can see, it's going pretty quickly. This will probably run in 10 seconds or less. But if you have a slower machine, or if you're a more complex model, then that could take longer. Right? So we'll scroll down. You get some error messages. All of these are more than fine. You don't even need to worry about them. All right. So this is, if you're familiar with latent profile or latent class analyses, you'll see the same thing with random starts. All right. And now we will scroll down to model data fit. So model data fit in Bayesian, they have their own way of evaluating model data fit that is different than the traditional frequentist way of doing so in structural equation modeling. But there's actually becoming a melding of the minds, and some recent research within the last 4 or 5 years. I think Asparouhov and Muthén have an article in 2021, and then there's another researcher in 2022 who talks about the application of our traditional fit indices, CFI, TLI, RMSEA, to Bayesian structural equation modeling. But initially, Bayesian SEM did not use these traditional ways of evaluating model data fit. Instead, they used the posterior predictive p-value. Right? And so generally, we want this PPP value to be between 0.45 and 0.55. Those are kind of some just general guidelines that researchers have talked about. And if I mentioned some of these articles, I will provide links or citations in the video description, so you can look at those at your leisure. So this actually tells us that we have a less than optimal model, that there's some potential problems here with the PPP value. All right, so again, we want this to be 0.45 and 0.55, and essentially we want these to be equally symmetric away from zero. So we would really want optimally this to be 15.073 rather than 25. All right, so it's giving us a little bit of feedback that maybe we don't have the best model. All right. But then we can contrast that with these traditional fit indices that those articles I referenced begin to talk about. And they're going to be really quite close to what we see in, again, in traditional SEM. So if you use SEM with maximum likelihood, then use Bayesian SEM and you calculate your CFI values for both, they're probably not going to be all that different. There are going to be slight differences in those values because there's different information that's going into the estimation. But for the most part, you're going to get something that's really, really close, right? So we're actually going to scroll down. And again, this is the main effects only model. Again, we can get a general sense of what's happening, but again, when we look through and add in that moderation or that interaction term, a lot of these things can potentially change. So I don't place a whole lot of weight on the significance or even the direction of these effects. But where we will want to go, much like in the maximum likelihood estimation model, we want to go and look at this explained variance. And so right now, um, uh, the relationship mindfulness at the dyad level and dyadic coping at the dyad level uh, um, by themselves and on their own, they are accounting for approximately 65% of the variance in dyad level relationship quality, and again, indicated by the female and the male partner, right? And then down here, we have our credibility intervals. So again, these are different than confidence intervals. Confidence intervals are, actually very difficult to interpret. And again, they give us a lot of really good information, but confidence intervals, very briefly, we aren't able to make probabilistic kind of inferences about confidence intervals, right? So confidence intervals, we can't use language around probability, okay? But one of the benefits of Bayesian is that we have what's called credibility intervals, and that's where we can begin to use terms, like probability. Whereas in maximum likelihood, we can say, we are 95% confident that our upper and lower bound contain the population mean, right? We can't say anything. The population mean probably is in between our upper and lower bound because, again, that population mean from a frequentist perspective doesn't move. It's a fixed value. Whereas in Bayesian, we can make those probabilistic kind of interpretations because we don't view that population mean as a fixed value. Rather, there's a distribution associated with it. Right. So again, we don't necessarily need to go into all of this, but I will scroll down just a little bit more to show you some priors, because I think that's one of the things that Bayesian does. And I'll also show you the Tech 8 output. All right. So the default for M plus is that Bayesian estimation will use what's called diffuse or uninformative priors. So priors, you can kind of view priors as, or think about them in kind of terms like of a meta-analytic approach, where we're running a study and we have our variables, and there's probably some research that has already been done on a lot of those variables even together. And so what we can do in Bayesian is we can insert information that that the researcher that we are bringing to bear into our model. So what Bayesian is going to do, it's going to integrate what the data is actually telling us along with the information that we are telling the model about what we believe to be the associations to be among the variables or the variances to be among the variables. So in other words, Bayesian is going to combine what the researcher knows through our specification of these priors, along with the data, and that's how we're going to generate our estimates and our confidence intervals and things like that. Right. So Bayesian is using, again, those two pieces of information, whereas in a frequentist perspective, we are really only using one. And so by default, we here are not inserting any prior knowledge. All right. And so, what's the benefit? Why would we do this? Why would we use Bayesian if we're not going to use uninformative prior, or we're going to use uninformative priors? Well, with Bayesian estimation, one of the things that makes it more attractive when you're getting into these more complex models is that it's more computationally efficient than maximum likelihood. So when we only have like one latent interaction in a model, like we do in this model, Bayesian and maximum likelihood, they both do fairly well. But the more and more complex your model gets, and the more and more points of integration, i.e., like the number of latent interactions that are in your model, the more and more maximum likelihood struggles, and the more and more Bayesian does better, is able to effectively estimate these models. So a lot of models that won't converge in maximum likelihood will converge in Bayesian estimation. So the kind of the idea here is that Bayesian estimation is more computationally efficient and can actually allow us to arrive at a converged solution. Also, if we have prior knowledge around what we believe to be true or what research has found, we can insert that prior knowledge. That's another benefit. For a lot of the Bayesian estimation, we are using, again, we can use it for more computational efficiency, right? So again, this right here, prior for all parameters, we can see that the prior mean is 0. So that means we are making 0 kind of inferences about the means of the variables, right? And as you can see, there's 6 right here. So these are the means of our 6 observed variables, and we didn't, again, provide no information about that, right? And then we'll scroll down to the Tech 8 output. And so here's going to be our Markov chains, the Markov chain Monte Carlo, one of the ways in which we obtain our parameter estimates and what's kind of going on behind the scenes. And what we're doing is we're actually looking for these different chains that we're estimating. We want them to converge. So M plus is kind of simultaneously estimating these different parameter estimates in these different chains. And we want those chains to eventually arrive at the exact same answer or something that's very, very close. All right. Because we want these independent chains of estimating the parameters to yield identical information, because then we can have more confidence that these are the best values that represent the distribution of the population. Right. And so we do that through this PSR kind of indicator. So you'll see at iteration 100, so after 100 after 100 iterations, our PSR is 1.194, which is actually not terrible, but it's not great either. We want this value to be below 1.05. And so we are going to estimate, again, 25,000, right? And we eventually get to our PSR value being 1.001. All right, so this is well below the 1.05, which means our different Markov chains, they converge. They arrived at a very, 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 very similar solution, which means we can have, again, more confidence that we're getting accurate parameter estimates, right? When this value is, let's say we come to iteration 25,000, we get a PSR value of 1.194. It means that we might need to increase the number of iterations. We might need to go to 50,000, but it also might mean that we have a misspecified model and we would find additional evidence above, again, with that posterior predicted p-value and those Bayesian fit statistics. Right. So if you don't have convergence, those are some things that you may want to check out. Another thing that I'll mention before shifting over to the model with the interaction is that we have information criteria. And so in maximum likelihood, we have the -2 log likelihood, where in Bayesian estimation, we have deviance, which is kind of essentially the same thing. And then we also have the BIC, which is the Bayesian information criteria, which we also have in maximum likelihood. And the posterior predicted p-value that I mentioned earlier, this is actually going to go away once we include this latent interaction. Right. But we will have these values from which to compare nested models. All right. So what we're going to do next is go into the syntax for the model with the latent interaction. All right, so we'll start here. And again, everything is actually going to look very similar if you just combine maximum likelihood syntax with what we just had. We are estimating Bayes. We are using type equals random, which is the same. Here, I am estimating 50,000 FB iterations. Again, I want to estimate more and more iterations. That increases the likelihood that our Markov chains are going to converge on a single solution. And it allows us to, again, just like bootstrapping, have more and more and more confidence that these are the accurate parameter estimates, right? And you'll see here, I have these parameter labels just like I did in maximum likelihood. If you watch that video, one other thing that is new here is this model constraint. So in the maximum likelihood video, I calculated simple slopes where we did plus and minus 2 standard deviations above and below the mean. And that essentially allowed us to estimate these slopes at different levels of our moderator, okay? And so what we're going to do here is rather than estimating those slopes at different standard deviation levels, because again that could be kind of arbitrary, right? Why is it 1 plus 1 and plus 2 and plus 3 or whatever it is? Why isn't it 0.77 and 1.52? Again, so it's kind of arbitrary, right? But we kind of think in standard deviation language within like structural equation modeling, correlations, and things like that. But what we can do here is actually obtain these Johnson-Neyman butterfly plots. And what these are going to provide us is at the exact moment, the exact value of our moderator is the relationship between our IV and our DV. Has it shifted? Does it fall from significant to non-significant, or non-significant to significant, or vice versa, right? So we'll be able to visually inspect the associations between our IV and our DV at varying levels of the moderator. And what we will do is we will detect significance through is 0 included in the 95% credible intervals, right? And so what we're doing here is we are, we're looping. So essentially what that means is we are going to repeatedly estimate the effect of our moderating variable, which again, in this example is going to be, again, relationship mindfulness. Again, it doesn't really matter practically what we use because we're, again, interaction terms, we're just multiplying things together. So in this example, we're using relationship mindfulness as the moderator. And what we're going to do is we're going to loop that from values of -3 to 3 in units of 1. So that's what these values represent. So what you'll see in the figure is that you'll see -3 and 3 are going to be those large and small values on the axes, right? And then you can create a arbitrary name, but essentially, this is essentially the slope. And so actually it'd probably be more accurate to do uh, cop, all right? And then what we're doing is we're creating that, all right? So actually, we're going to do this, changing up the names to be consistent. All right. We're going to plot this dyadic coping beta across varying levels of relationship mindfulness. And this is this, you'll notice up here I have A and int. Again, what you'll notice is that up here, I'm using those values to create this equation where we're continuously looping the values of dyad level relationship mindfulness onto the couple level or dyad level relationship quality at varying levels, right? So what we'll do here is I'm not going to run this because it actually takes a little while to converge, but here is the output that you would get. All right, so it takes not terribly long. It only took a minute to converge, but it will it does take a little bit longer when you're estimating latent interactions. The models do take longer to converge. So we'll scroll down. Right? Again, you're going to see this. Again, we have a large number of FB iterations, so at this point we can kind of ignore this. And what we'll do here is look at our unstandardized results, and we have a significant interaction term, not surprising, and it's negative 1.2. Right. So this, you will notice slight differences in the results between maximum likelihood and Bayesian estimation. I believe in maximum likelihood, this was negative 1.3. So we'll see that the slope's a little bit smaller here, but essentially it's kind of telling us the exact same story, right? And so here is our parameter estimate. Here is the posterior standard deviation. You can kind of think about this as like the standard error. We have a one-tailed p-value, so don't trust this. Again, this is only one tail. And then we have our 95% credibility interval, okay? But we actually don't want to look at this credibility interval. We actually want to scroll down and we want to use this credibility interval instead, all right? And so this is where I obtain the significance test. So we see that the interaction is significant, and we have a 95% credibility interval of negative 168 to negative 703. And if you really want to brag in your manuscript, you can actually say 99% credibility interval. It's significant. So we can say with again a high degree of confidence, or now we can say probability, that our effects are significantly different from zero. And then we also have our explained variance. All right, so our explained variance in this model is 0.18 or 0.815 or 0.82. So again, the interaction term explains a substantial amount of variance in our dependent variable, and overall a model with three predictors is explaining nearly 82% of the variance in relationship quality, dyad level CSI. All right. And so what we'll do now is I'll actually show you the loop plot. So I'm on a Mac here. So in M Plus on the Mac, it does not come with a diagrammer feature. So you have to use a Windows computer in order to obtain these plots, which is kind of annoying. I kind of wish M Plus would kind of step their game up with Mac. But luckily I have another machine which I ran the plots. And this is what it looks like. So this is that Johnson-Neyman plot that I had mentioned. So oftentimes they're called butterfly plots. So the red is the slope of common dyadic coping at varying levels of dyadic relationship mindfulness. All right. So you can ignore this. This would actually be the common fate, CFM beta. But as you see, I didn't change it in the original that I estimated and ran before starting the video. So that's why that's up here. But yeah, this is the slope here. So we can see, as relationship mindfulness values increase, it gets bigger and bigger and bigger and bigger and bigger. The effect on, again, common dyadic coping gets smaller and smaller and smaller and smaller and smaller and smaller. All right. Well, where does it exactly become significant or non-significant? Well, we know if the zero is contained within the 95% credibility interval, it is not significant. So that means we can just find zero and then just move our cursor over. Again, this is a very rough guesstimate, and there's more precise ways of doing this, but roughly around, like I don't know, 0.80 standard deviations. Again, I'm kind of, again, ballparking it there, but that looks about 0.80. That's when it becomes non-significant. All right. And zero is now contained within that credibility interval. All right. But if we look, and we can look on the other side of this won't always happen, but it becomes significant again right here around 3 or 3.5, I should say. All right. And so again, this provides a little bit more nuance in the estimation of our effects, right? So we can say around 0.80 standard deviations and above 3.5 standard deviations, the effect of dietic coping or common dietic coping differs, right? It's non-significant, right? So again, this again provides a lot more information, a lot more nuance. And if you're using a scale, I've created these butterfly plots for papers where I'm using like the CESD, and that's actually a scale that a lot of clinicians will use in their own screening process, or the PHQ-9. And so, this is where I kind of like using the original metric, even if it is kind of arbitrary, where I can say scores on the CESD above 12 and below 20, that's when the slope is non-significant. All right. And so that actually gives clinicians some usable information. So again, sometimes even though we might not like the metrics of our scales and they might be arbitrary and we just kind of have to create them and they don't naturally occur in the world, they can actually be useful to clinicians who are using these scales. So again, I'd pause people who just want to use standardized effects and standardized interpretations because there's actually potentially some value in some of our research questions that have more applicability to clinicians or people who are actually going to be using the scales that we're using in our own study. So the more we can use scales that clinicians use and vice versa, the more and more research can inform clinical practice through, identifying at what points are the associations significant using this specific scale, right? So this is a butterfly plot, and you can kind of get a sense of what it can provide, right? And again, you'll see it's not a smooth kind of parabola. It's kind of a little jaggedy in certain places. You'll see like right here, it's not smooth. It's kind of going smoothly and then it bumps up a little bit and then it kind of wiggles back and forth. That is perfectly fine. That is really, really normal, especially out on the perimeter, out on these more extreme values because we tend to have fewer cases out here, which means we have a lower standard error or lower posterior standard deviation, which means our estimates are going to be have more uncertainty in them, right? And that's why you see the confidence interval be really, really tight here because we have a lot of people here in the sample and it gets much, much wider out on the edge because we don't have as many people on the extremes, kind of by definition of the distribution, right? So hopefully this video has been helpful and has provided a little bit of background into estimating the common fate moderation model using Bayesian estimation and taught you a little on how to generate these butterfly plots. Thanks so much for stopping by and see you in a future video.